Okay, so thanks for having me here. My name is Albert Jonathan. I'm still a PhD student here. I'm working with Professor John Weisman and Professor Abhishek Chandra, but Professor John Weisman unfortunately cannot come to give the talk today, so I'll be giving the talk on behalf of him. Okay, so the topic that I'm going to talk today is about our work on geo-distributed data analytics using an edge cloud system. Okay. So traditionally, when we talk about big data analytics, we usually consider a data center, cloud, or like HPC cluster environment, right? Where there are a lot of computational resources, and we have high-speed network that are interconnecting all the resources. So in such an environment, you can run data analytics with high performance by exploiting the collocation of the compute storage and the data. But in recent years, we have seen that there's an increasingly emerging data analytic applications from companies that actually rely on data that are geographically distributed, because the data itself is by nature born in a distributed fashion. So just recently, Microsoft reported that they frequently need to analyze their Skype user logs that are distributed across hundreds of servers all around the world. And similarly, Facebook and Twitter also mentioned that they constantly need to process hundreds of millions of new data on a daily basis. So yeah, for a large company like Facebook, Microsoft, Google that operates hundreds of servers all around the world, it is for them to analyze their data that are located on servers here. And if you look at the data analytic processing that they are doing, we can identify there are two dominant computing paradigms. First one is batch analytic, where they need to process the data as a batch every day, week, or month. Also, sometimes they need to process data in real time as new data arrives. So that's streaming analytics. And both types of these analytics are considered as high performance problems because we need to process them with high throughput and low latency. So let's see how we want to sample how we can process this geo-distributed data. So one way is we can use a cloud, like we can use Amazon cloud here, but then we have some animation here. So if we try to use cloud here, we need to transfer all this data from different location over the wide area network. And if we look at this illustration here, we need to transfer one of this data, which is 100 gigabytes, it's not very big, over like 20 megabit per second bandwidth. So if we do this before doing any data processing in the cloud, it will take like more than 10 hours. So clearly this approach is very inefficient and also not acceptable for most data analytics applications. Alternatively, we can also try to utilize any computational resources that are located close to the data location. So we call these resources as edge nodes, and we call the system that uses these edge nodes as edge cloud. Although the computational power that's provided by the edge nodes may not be as powerful as those of data center or cloud, we can still use these computational resources at the edge to pre-process the data. So we can do some data aggregation or filtering any unnecessary information. And typically this will result in a significantly reduced size of data. So if we consider the same network bandwidth from the previous illustration here, we only need to transfer 1 gigabyte of data over the bottleneck link. And this will significantly reduce the overall time to process the data. So we see from the previous example that we can use edge cloud system for processing geo-distributed data, but the main challenges for an edge cloud system is because of the wide area network itself. So as we know, wide area network is highly heterogeneous. If you look at this graph here at the bottom right corner, we did a measurement on bandwidth between servers in Amazon EC2. And we see that one bandwidth link can be as high as, one link can provide as high as 10x or up to 20x more bandwidth compared to the slowest link. Also, wide area network has limited bandwidth and higher latency compared to the intra-data center network. And they are also expensive and highly dynamic in practice. So we've just covered the background and the motivation of distributed analytics, and then we'll now look at the challenges of batch and streaming analytics in wide area environment. So in the case of batch analytics, the main challenge here is how we can extract information from large amount of data that are geographically distributed. So example of this type of analytics include like analyzing user logs for advertisement choices. So we can do this in a batch in a monthly basis, say. But one of the main challenges here is one of the questions that we need to address here is how can we deploy a batch job in a wide area environment? So the goal here, we want to do the processing with in a timely manner. So the goal is to minimize the end-to-end processing time. So we model a batch job using a MapReduce execution model, where the mappers will read inputs from multiple sources that are geographically distributed. And then the reducer will read the output of the mappers once the mappers finish. And we identified that in geo-distributed data analytics, usually the main bottleneck is in transmitting a large amount of data over the limited one bandwidth. And this happened during the mapper phase when it reads inputs from multiple sources that are geographically distributed, as well as in the shuffle phase. So we implement a one-aware job scheduling, where we try to identify where to schedule each of the mappers in the edge nodes here. And we also try to optimize how can we schedule the reducer and the mappers together. Because if we schedule the reducer after the mappers finish, we may not get a global optimal deployment. So we did a optimization, we did an optimization that tries to optimize the whole mixed-span of the MapReduce execution in wide area environment. In the case of streaming analytics, the main challenge here is how can we extract information in real time from continuous unbounded data streams, and we want to this in a real-time fashion. So the example of this kind of analytics is detecting trending topics from multiple social network data that are stored in distributed servers. So similar question that we need to address in streaming analytics is how can we schedule the long-running stream operators in a wide area environment? So we also did a one-aware operator scheduling, where we try to figure out where each operator in the streaming topology should be placed in the system. And our goal here is to minimize the delay, because we need to process data in real time. Also try to save one utilization and achieving high throughput execution. But sometimes we cannot get an optimal decision for all of these metrics here. So we also did an optimization where we try to optimize the trade-off between staleness and one bandwidth utilization for streaming analytics under certain constraint. Also, we also did some optimization to achieve high throughput execution for multiple streaming job execution in wide area environment. And in addition of achieving high performance execution, if we talk about streaming analytics, we also need to handle runtime dynamics, because most of the streaming jobs are long running. So the system should adapt to a changing environment, which may happen because of the workload change or network bandwidth change or even occurrence of failures. So we are currently looking at how we can scale out a streaming operator in real time with little overhead. So if we look at this example here, say if the bandwidth between A and B becomes a bottleneck, we may want to repartition the data stream just to balance the workload, or we may also want to completely migrate the operator from one location to another location. So this is just a brief discussion on data analytics in wide area environment. And then the next slide, I'm going to talk about one of the edge cloud system that we have developed at the University of Minnesota, which we call Nebula. So Nebula is an edge cloud system for geo-distributed data analytics, and we currently use a combination of both volunteer and dedicated nodes for the compute and the storage nodes. And basically Nebula treats all of the nodes in the system here as one single logical data center. However, the system is aware of the highly heterogeneous network links that are interconnecting all of the nodes here. So just briefly mention some of the core components of Nebula. So it has a monitoring module that periodically monitors the bandwidth between nodes, and then it will share the bandwidth information to the other Nebula components for implementing the one-aware policy. And there's a distributed storage master that determines data management policy, like where its files should be placed in the system, as well as ensuring the availability of all files. And there's also a resource manager here that's doing something like what Mesos and Yarn do, basically to share all the computational resources among multiple analytic frameworks. And Nebula provides a web interface where application writer can submit their jobs to the system, and they can also monitor the task execution in the system. Also, we use a web interface as well for volunteer nodes to join the system. So when we are designing Nebula, we keep in mind how we can make the system easy to use for volunteer nodes, which can be any machines like desktop or cloud lab at ISP. And we also want to ensure that all the volunteer nodes are safe from malicious programs. So we run all task execution inside a native client sandbox, which adds like 14 to 16% overhead. By having this dispersed machine around the world, Nebula allows data processing at the edge, just like what we saw in the previous example. And it also allows users to access their data with low latency, because we can store files close to where the user frequently access. And we also add support to allow multiple computing frameworks to be ported easily to Nebula. So one of the framework that's most mature, I would say, is the Batch Analytic, where we implement a MapReduce framework on top of Nebula. And we are also currently trying to port a streaming analytic framework where we take Apache Flink. It's an open source streaming processing system, and then we try to port that on top of Nebula as well. And we also try to support mobile and IoT computing on top of Nebula. So just show one of the results. This is the result of running a MapReduce job in Nebula, where we compare the different edge system here that stores the input or the intermediate data in the centralized location, and then we compare the MapReduce execution with Nebula. So we use 52 Planet Lab machines that are geographically distributed across the US and Europe. And in the y-axis here, we have the runtime, so lower is better. And we can see that Nebula can achieve up to 7x lower than runtime, because this is because of Nebula is aware of where to put the task close to the data location. Also, we did a little bit of experiments that shows that Nebula can gracefully adapt to failures, both in the context of compute node failures as well as data node failure.
No, ಇದು ಅಟೆಂಡ್ ಮಾಡೋದು ಯಾವ್ದೋ ಕಾನ್ಫರೆನ್ಸ್ ನಡೀತಾ ಇದೆ analytics.
Just quickly go to the conclusion. So we basically talk about the challenges in the distributed batch and streaming analytics in wide area environment. And we believe that edge computing will play a pivotal role in geodistributed data analytics. And basically Nebula project is focused on this opportunities here. And I also want to briefly mention about other works that our group has been working in the context of wide area environment. So we also work on a geodistributed storage system, and we also recently published a paper on mobile edge computing that we use on Nebula. Ongoing work, we try to to support IoT processing on Nebula, and just recently we also look at the opportunity of geodistributed that we can port on Nebula. So with that, I would like to thank you. Happy to take your question.
Right, great. So I think our guest speakers handle things very well. We're only 5 minutes late for your lunch. Apologize. It's one of the hard things. You're pretty good. So maybe you can take one question, then
sure. Or yeah, if anyone has a more detailed question, we can also take it offline.
I'll ask a non-detailed question, which you can finish offline.
Okay.
Is there any distribution that we can play with now, or have you released anything?
So we have the that we released, but we are still debugging it. We'll only have the batch framework ported on top of the Nebula, and yeah, we'll try to port the streaming as well later on.